So you guys saw my email. The next test is next Tuesday. I posted the review problems, and I stole a review sheet from another school that covers the same stuff. So for those of you who want extra problems, there's even more. They're more different. Of course not. You don't get answers.
What school did you steal it from?
Do you have answers to the review questions?
No. Well, get a study group. If like 5 of you have the same answer, that's probably right.
Look, I did homework number 10 twice. I didn't even homework number 10 twice.
Remember those guys?
Of course. I showed this to my friend, and then I'm going to watch him be like, oh my god, this might be kidding. What is this called?
Alright, now obviously not everything here applies. For example, you can ignore problem 21, you'd ignore because we did that on the first test. 22 you can also ignore because we did that on the first test.
23?
Wait, I didn't get that paper.
21. Everything is
So we don't have a similar test like this.
So you can ignore 21, 22, you can ignore...
I didn't get one either.
Yes, it's only chapter 2 for the next test.
So we ignore 21 and 22.
Ignore 21,
I see
22.
people use this fun everywhere.
Why did you say something like that?
I didn't get one.
You can ignore problem 31 as well. You can ignore problem 35. You can ignore problem 38. There are no problems on linear approximation or related rates, but you'll get plenty of practice on that on the review problem. You can have this copy. Oh, there are more. It's just for extra practice.
Anything to impress me on my
So today we're going to finish 2.7 and maybe 2.8, hopefully 2.8. On the homework part? Negative sign. You only make these negative if you know they're decreasing. Positive if you know they're increasing. Yeah, it just depends on how. So you know it's like north, west, east, south. So if you're measuring something and it's moving north, if you're measuring its distance from a certain point, then if it's going in this direction, you make negative. It's going that direction, positive. But it's just because of how it is. If the point was here moving that way, then this would be negative and that would be positive. You have to look on increasing decreasing. You don't look at direction. Right? Rates don't depend on direction. They depend on increasing or decreasing. That's the only thing. So. Okay, so I believe we have one last problem here. Problem 6, the baseball bat.
You forgot to do one of the questions that had a tangent line.
Which one was that? Which one was
Actually,
that?
never mind. It might have been 2.6.
Yeah, I think that was 2.6. Yeah, we're only left with problem 6 here. It's actually a problem from the book. I forgot what problem it was. Problem 18 or something like that. But but it's a nice problem. So it's problem 6 on our handout. So you have a baseball diamond is a square with side 90 feet. So you know this is 90. This is also 90. And a batter hits the ball, runs towards first base. So I don't know how much you guys know about baseball, so I'll probably have to tell you guys about it. This is called home. This is where the batter stands when he hits the ball. This is first base. This is second base. This is third base. So the batter would be here, you hit a ball and start running in that direction, right? So he hits the ball, he runs towards first base, and we are told that what his speed is, right? And now we're asked, at what rate is his distance from second base decreasing when he's halfway from first base, right? So pretend that the runner is running along here, pretend he's like here, right? This is the runner. Okay. Now what do we want to measure? We want to measure his distance from second base, right? Which is this distance here. So I can call that something, maybe y. And it also mentions his distance from first base, right? When he's halfway to first base. So I probably call his distance to first base something as well. This is of course 90. This is of course a right triangle, because it's a square. So we read the problem. Step 2 was to draw a diagram. This is the diagram for part A. Now we're going to write down what we know and what we want. What do we know here?
That the side is 90 feet. Because this square at the side is 90 feet.
Yeah, we know it's 90 feet. That's in the diagram. That's good.
The speed is 44.
What speed is 44?
Dx of dt.
So we know that dx dt is what? Actually, what's dx dt?
Distance of the time.
Nope. 5, no. Where did that come from? No. Huh? Minus 24. Why is it minus 24? When he's moving towards first base, x is decreasing. The rate is minus 24. Right? Okay. Now, so we know that. What do we want?
The distance between the runner and second base.
We want dy dt when x equals 45. So right now what we know, what we want. Okay, let's move on. What was the third step? We have to come up with an equation. What's the equation here? Pythagoras' theorem. This is a right triangle here. So what can we say? Alright, sum of the two legs equals the sum of the squares of those. So x squared plus 90 squared equals y squared. Okay, so the next step is to differentiate implicitly with respect to t. What do we do here? Plus 0 because that's a constant. And cancel the 2's. we know we want dy, we can solve right here. dy dt would be equal to x dx dt over y. Now, do I know everything that I need to use here? I know that x should be 45, and I know this is minus 24, but what is y?
45 over.
So we guys need to find y. So just go back to the original, right? We have 45 squared plus 90 squared equals y squared. This is, of course, 90 is 2 times 45, right? So you can think of 90 squared as 2 squared times 45 squared. In other words, 4 times 45 squared. So on this side, you have 5 times 45 squared, which means your y is just 45 radical 5, right? So now we can go back. dy dt equals x is 45, dx dt is minus 24, and now the y is 45 radical 5, these two cancel, minus 24 over radical 5. So the distance to second base is also decreasing. Which if you think about it, it makes sense because your hypotenuse and it's turning into one of the legs, which we know is smaller than the hypotenuse. So that actually makes sense. Any questions here?
So when we do this, pretty much we get the derivative of a function?
Yes. So a few people have been telling me they were confused by related rates. One way to just keep everything in track is to really stick to the steps that I gave you in the previous one. So you could realize here, I actually followed the same sequence of steps. Step 1 was I read the problem. All right. Step 2 was diagram. This is step 3 right here. Just write out what you know, what you don't know, because you're going to use it later. Step 4 is coming up with the equation. Step 5 is actually differentiating. And step 6 is when we start to plug in everything we know and solve for what we don't know. And sometimes there's going to be a guy that we still don't know at this point, where we can just go back to step 4 and find it and then come back. So this here would be step 6. So it's very important for you to keep clear that you're really always doing the same 6 steps, no matter which problem you're doing, right? Sort of helps you keep focus and you just know what you're doing and just find it out. And if you go over the problems that we've done before, all the other problems, you'll realize that this is always what we've been doing the whole time. So that was part A. Are there any questions before we move on? All right, how do we do B? Okay, so we read the question, and we're going to draw our diagram. This is home, this is first, second, third. Guy's still here, moving in that direction. So what are we trying to measure this time? Distance from third base as he's running towards first base. So how are we going to set up this equation?
Would the answer just be the same, only 24 will be positive?
Yeah, that's what it's going to end up being. So you could actually tell that from the beginning because you have a sort of symmetry here. So you can see by symmetry, the same place that this is decreasing, going to be the same pace at which that is increasing. So yeah, it is going to end up being that. But if you didn't know how you solve it. We could actually maintain the same labeling there, or we could relabel this x and that y if you want. So it's really up to you guys. So what do you guys want to do? Relabel or just? Huh? You want to relabel? So you want to call this x, that y? This would be 90. So it's going to look pretty much like the same problem. The equation is going to be this squared plus that squared. We actually haven't gone through the equation yet. After the diagram, we're going to write now what we know. What we want. This time what we know is that dx dt is equal to what? Positive 24, because in this situation the x is increasing as he's moving. And we want dy dt when x equals 45. So the equation is going to look exactly the same. Then the next step is to differentiate. We're going to get this. dy dt is going to be equal to x dx dt over y. X is 45. This time, this is a positive 24, and this is going to be the same thing. So yes, we've confirmed our suspicions that it gives you the same thing.
You still have to do all the steps.
What are all the steps?
You don't have to do all the steps, you just know that you're going to switch negative 24 over 24.
Yeah.
But so it's not required in a problem like this, came up on steps, to do all the steps again.
Well, no, like the problem on the test, I wouldn't actually do part A and part B. I'd actually do something completely different for part B. Yeah. I guess the point of this is to get you to just practice going through over and over. And that ends related rates. So the homework for that is due on Thursday. Any questions, concerns before we move on?
The homework on the website associated with that?
I believe so, yeah.
It says it's Tuesday.
Huh? Test is next week Tuesday, yes. And the review problems are already on the website, and I just gave you.
No,
Yep, you have another question?
No, because the web is on for 2.7 students.
yes.
Are you sure?
Change it.
I'll change to Thursday. I thought I'd change it.
So you're going to finish 2.8 today, and then Thursday's going to be a review day?
No, Thursday I move on to chapter 3.
You're kidding.
Already your review.
What about 2.8?
We're bitches now, right? It's going to be review.
You should have moved on to chapter 3 though, we're taking the test on chapter 2
You
still.
have a strong foundation.
It's like what you did with the quiz. You gave us 10 minutes for the quiz, and then you went on to chapter 2.6. Like, what?
Yeah, we didn't have time to think for the quiz, but that's.
Exactly. When you're in a final, you're not going to have time to think either.
Yeah, we did. Well, we have 3 hours.
No, it's like, yeah, 3 hours.
You have 2 hours.
Whatever. Like, you have time to plan out that. No, let's have her review on Thursday, please. No, nobody's
We'll
gonna
see.
back me up again.
I'll make you up.
See?
Friday we have a quiz on up to 2.8.
Which is very important this week.
I'm so glad we don't have some things.
Tuesday.
One more night.
After you have a whole long weekend.
We have a quiz this Friday.
Yes.
We already learned chapter 3.
Yes.
No, he just said that for the sake of saying it. Just so glad we have class on Wednesday.
There's anger in that voice.
Okay. So I wrote down a lot of notes for this, but I don't think I want to rewrite this. Let's give you the basic idea. we have a function and we're at some point A, f of A. In terms of the notation of A and f of A, can you tell me what the tangent line to this function at this point, what its equation would look like? If you wanted to find tangent line, how would you do it?
Y minus f of A.
Call this, this is just f of x. So what would we do? We know that the slope would be f prime evaluated at the point of consideration, which is A, right? And then we do what? Y minus y1 equals n x minus x1, right? In other words, your y is equal to f prime of A, f of A plus f prime of A times x minus A. This is the equation for the tangent line, right? So this is y equals f of x. This is y equals f of A plus f prime of A times x minus A. So now here's the situation. Let's say our function was really complicated and it was just a real mess to get values from this function. A straight line is really easy to get values from. The idea is we're going to want to approximate the values of this function with the tangent line. It turns out that the closer we are to A, the difference between the tangent line and the actual function becomes nothing, right? So if we're over here though, we're really far, the distance between the function and the actual tangent line, there's a big difference in the y values. But as we get closer to A, their values get closer together. So the idea is we're going to want to approximate the function with the tangent line by getting close to A. And it's not going to be the sort of situation like a limit. You're sort of going to want to pick values that are really nice, that you know how to evaluate the function at. So the idea is when x is close to A, our function gives us almost the same value as the tangent line gives us. This is called a linear approximation. Right? Because you're approximating the function with a linear function, a straight tangent line. Right? The function L of x equals f of A plus f prime of A minus A is called the linear approximation of f at A. Mechanics, x is a value that you want to approximate f of x for A is a value close to x for which you already know f of A and that's the idea. We're going to apply it now. linearization here. Let's say this here is your x value. The difference between, the actual difference between these two y values is called delta y, the change in y. The difference between the value and the tangent line, that's called dy. Right? That's the difference between dy and delta y, right? This is the actual change in values. You take this y value minus that y value, you get the difference, right? The difference between the tangent line and the y value, that's called dy. That's sort of where the derivative comes in. And the closer you get, the closer they start to match. So I think your homework might use that notation. That's the difference between delta y and dy. But let's actually put this to use so you can see what the heck I'm talking about. I want to find the function that approximates sine x with a straight line when I'm close to the point of pi over 6. Recall, we just did it. This is the linearization. And what is it equal to?
A plus f prime base minus x minus a.
Here, f of x equals sine x, which means that f of a is just f of pi over 6, which is just sine of pi over 6, which is guys are taking too long. F prime of x would be equal to what? Which means f prime of a is just f prime of pi over 6, which is just cosine of pi over 6, which is 2. So this means L of x is simply f of a plus f prime of a times x minus a. So that is a straight line that approximates sine at that point. So this is your sine curve. Pi over 6, that's our a value. The equation of that tangent line is actually y equals 1/2 just radical 3 over 2 x minus pi over 6. And when we're close to pi over 6, the difference between this and the actual sine function is very small. So I can actually use the values on this line to approximate the values to sine when I'm very close to this point. So this is the answer. That's just an illustration. So a possible question on an exam could be this. Find the linearization of a function. And I told you at what point. I just need you to fill out this form. Take the function, find its derivative, plug in the points, and put it in the form. That's it. Yeah, linearization is usually not the differentiation is the hard part. But usually it's the functions in these problems aren't hard either. Like, it wouldn't give you something crazy. Another example of function would, a question would be something like, use linear approximation to approximate the radical of 3.9. Yeah, do you 3.9 or 3.99? So this is a very common type of problem. You'll see this on a lot of the finals, and it's highly likely that I'll actually ask you a problem like this on the test.
What is that, unlikely? Unlikely.
Highly likely. Like if I ask you that's part A, this is part B, or something like that. So the idea with linear approximation is, of course, you need a function to do all this stuff with. So we're really going to base our function after the thing we want to approximate. So what do you think we can make the function?
1 equals radical x.
Take f of x equals radical x, right? We want to approximate f of 3.99, right? That's really what we want, to approximate at the x value, right? So remember what I wrote out over here? X is that value that you want to approximate it as. What is your A? It's going to be a number that's close to this that you already know the values for.
4.
4. Radical of 4 is pretty easy. We already know radical of 4 is 2, so that is a nice number, right? So you see something like this, you're going to take a function that will look like that, where you're looking for some value to be plugged in, and you want to approximate what the value is. To help you out, you're going to start with a value that's close to that you already know the values for, right? And we're actually going to use that to help us approximate it, right? So now we note one of the other equations I mentioned. F of x is going to be approximately f of a plus f prime of a times x minus a. Since f of x is radical x, this means that f of a is just f of 4, which is radical 4, it's 2. F prime of x what's the radical x? Huh?
1/2 x negative 1/2.
Right. 1 over 2 radical x. This means f prime of a is just f prime of 4, which is 1 over 2 times radical 4, which is 1 over 4. This means radical of 3.99 is going to be very close to f of 4 plus f prime of 4 times 3.99 minus 2. Right? This here is our f of x. The x is 3.99. This is f of a. This is f prime of a. This is the x value minus the a value. Right? I'm just using that one. F of 4 we found that's 2. F prime of 4 we found that's a quarter. 3.99 minus 4 is minus 0.01. So what's that? This is 2 minus, this I can take to be like 0.25 times 0.01. So this is 2 minus, what's 0.25 times 0.01? Points. Huh? How many zeros is it? So what's 2 minus 0.0025? 1 point?
0.00.
It's 9975.
Yes. Would you ever include a question like that on the test where it requires like numbers?
By the way, what is actually the radical of? Yeah, let's actually do this. Square root of 3.99. Actual answer? Is 1.9974984. Right? So you can see it's a pretty accurate thing, right? And it's pretty accurate because I was only off by 0.01. Of course, if I was off by less, it would be less accurate.
How many decimal points do you need? I mean, how many significant figures?
Oh my god, don't bring that up.
It don't matter, it's whatever.
This is math, not chemistry.
No, I know, but I mean, so the fastest one.
I don't particularly.
So if we put 2, that'd be okay?
That's what I mean, you know?
Yeah, but how would you put 2? If you put 2, you'd actually get 2.0 as the answer. Which is sort of like, it doesn't show you like, oh, man, that's sort of weird. Yeah, but you can see it's actually pretty close. So you have a calculator. You linear approximation. What's the square root of 3.9? Everyone's whipping out their calculator. 1.997. Holy crap, how did you do that?
So we could have done that for one time?
Yeah. Of course, in practice, you wouldn't really do it for a function as simple as that. You really use this for really complicated functions that you have to use computers to work out, and you want to cut down on the lines of programming, so you just say, hey, instead of using the function, use the tangent line, and just try to get close to the point I want. And so your computer can run through thousands of calculations lightning quick, because it's only computing in a straight line. So that's sort of the application. You know, it's just to cut down on computing time. And these are really simple functions. In practice, we don't use it for this function, but it's just to illustrate how the thing will work. Okay, very similar problem for you guys to try. Let's get through this quickly. What would our function be? Cube root of x. Cube root of x. We want to approximate f of 8.01. Take a equals 8. So f of x equals the cube root of x means that f of a equals f of 8, which is just the cube root of 8, which is 2. So it means that f prime of x is one third x to the minus 2/3. This means that f prime of a is just f prime of 8, which is 1/3 8 to the minus 2/3. Right? Cube root of 8 is 2, raised to the minus 2, that's 1/4, so this is 1/12. This means cube root of 8.01 is approximately 2 plus 112 times 8.01 minus 8. This is
2 is f of x, right? Not f of a? Or does it matter?
2 is f of 8.
Okay.
Right, f of x we don't really know. X is the 8.01.
So then, sorry, because the formula is f of x is equivalent to, or like, whatever approximation to.
Right, the formula is f of x is almost f of a plus f prime of a times x minus a. So here my x is 8.01, which is what I want to approximate. Here I plug in f of 8, which I know is 2, f prime of 8, which I know is 112, and 8.01 minus 8, which is x minus 8. So this is 1 over 12 times 0.01.
Will we have a calculator on test to do that?
Nope.
So how do we?
Can we just write the fraction of the sign?
Yeah, you can just write as a fraction.
Yeah.
Something like that. So 1200 times 2, this is 2401 over 1200. I mean, that is the approximation. I don't think my calculator can do a cube root.
Okay, fine.
Turn sideways and make sure we stop.
Turn side. Did you find it?
I just have the basic one.
I'll do it.
What year is it?
This doesn't count.
2.000
2.00.
0 8 3
The actual answer.
Oh wait, crap. I'm sorry, that was the actual answer.
Okay, so the actual answer.
Wait, no, that was the right one. I meant to do the other thing this time. Yeah, I'm not right. 3 of 8.01. 2 points.
You're saying the actual?
Yeah, I'm done after 2.000 83296 86. More than. Yeah.
Alright, so we got it up to the first 5 decimal places.
Yeah.
So you can write either that decimal or that.
Yeah, at least you can answer that as each.
Okay. Can you write the decimal language or like how does it?
If you want to go through it, sure. You won't have a calculator, remember. You actually want to divide those and write that.
Again,
No. At least give me this first number. Jeez.
How are we supposed to get to that point?
This is the answer.
Use the fractions.
I would leave it here. If I were taking the test, I would.
And you want all this work, you can't just write it.
No, you can't just write that. You have to like show me this. You have to show me that you're doing this. You have to show you took the derivative, evaluate at the point, then that you plugged it in this formula, and you got that answer. Yeah, that's pretty much it. And then there's a section on differentials. It's pretty much the same thing. You're just using different notation. But differentials really takes advantage of the Leibniz notation. Recall that dy dx is just another way of saying f prime of x, which means that you can say dy is equal to f prime of x times dx. But remember, this is like a change in y. Measured by the tangent line. And this is the corresponding change in x. They are approximately equal to delta y and delta x when we are close to the x value. And the idea now is that your f of x is going to be approximately equal to, again, you base it off a value f of a plus, so this is like some old y value. And this is plus the change in y. But by this formula, you can see that I can replace dy with f prime dx, and it's exactly the same form as before. It's just using a different notation for the derivative. That's pretty much it. Let me show you how a problem using differentials would look to write out. Something here like using differentials. What's the volume of a cylinder? V equals Okay, so now how we actually get to this is we actually try to differentiate. The differential of v would be equal to differentiate this guy. It's very similar to like 2 pi r. Right, so you do a sort of product rule thing, and you add the differentials. I just do the derivative of v, here to the derivative of r, here to the derivative of h. Right? These guys are called differentials. Right? And we know the radius is changing. We're assuming the height isn't changing, so this we can assume to be 0. And we're only looking at this part. And so now, the radius we know is 20 centimeters, but we could actually be off by some change being 0.01. Did I say the height? That's the height. Just to get a number, it's not important. Just 4 pi. Think of this as a change in volume. In fact, that is our error.
Why is DH 0?
The height isn't changing. Its rate of change is 0.
So, okay. So only DH is 0, H is not 0.
No, you have a cylinder, it has some height, right? But the radius is getting bigger. We're assuming the height is staying the same. So the rate of change of the height is nothing. It's not changing, right? But dr is changing by this much.
When you get pi radius squared in the first equation for dv, like pi radius squared would be.
It's like the product rule. I differentiate with respect to r, then I differentiate with respect to h.
Alright. Okay.
And that's it. B. Relative error is just the error over the total value. It's just like what percentage of the total is the error. So this would be like 4 pi divided by the actual volume. Over 400 times 10. Any questions about this?
For these problems, you could also follow the related rates steps, right?
Well, not really. You're not thinking of them as changing with respect to time. You're just thinking of them as changing with respect to each other. Like the time quality is not changing.
Is that why there's nothing about their degree? It's just
Right.
because it's not like changing in relation to.
Yeah, we're just looking at like delta V, delta R, delta H. That's sort of how we want to look at it. But
Is this usually going to be the case where you could cancel out one parameter, like pH?
well, it would depend on the problem. They might tell you that the height is also changing, in which case, so I only know the derivative is 0 because I'm not assuming it's changing. There is no change in the height. The height is just 10. Yeah, that's sort of it. That's 2. That's all.
How do you know that 4 pi is the maximum? You find an error.
Because this is the most, I think this is the most I can be off by. I put the maximum possible error in my measurement.
Someone said minimum, you put 0.
Yeah, minimum would be actual value. Or anywhere in between this, I would have an error, but it won't be as much as it could. The worst case scenario is I could be off by that. I guess we can stop there. Maybe on Thursday we can do a little bit of review.